One of the units that's really common in environmental chemistry, but that we use almost never any other time in chemistry, is parts per million, parts per billion, and those kinds of units. And although these are initially kind of awkward, and before now I've always had to look up how to do the conversion every single time because I do them so rarely, it's good to remember, if you can, that they're really just analogous to using percent. So when we think about percent, we use this all the time. We don't always think about the fact that this is parts per hundred. Even though we use it instinctively, it's not always in our brain. So if we say 6%, we really mean that that is 6 over 100. And this is, in fact, the calculation that we do if we want 6% in decimal form. So we could, for example, take, what's 6% of my 12.85 gram sample? So we can easily do this calculation, and that one is super familiar. And we would just put in our mass, and then we would get our proportional amount of mass. So when we look at using parts per million, one of the situations that you might see it is, for example, in water quality. Now, each year, my water utility sends out a quality report for our water, and they list amounts of different things that are or mostly are not found in our water. So let's look at a few of those water quality standards. So when we look at water quality standards, we have two standards. We have what's called a secondary standard and a primary standard. The primary standard is the one that kind of is the, stop sign, no, except that that's a hexagon and not an octagon. But anyway, you get the idea. So primary standards are where action needs to be taken. So if the levels of whatever it is that we're looking at are higher than that primary standard, then we have to do something to remediate the water. The secondary standard is the one that we'd prefer to keep our levels, whatever they are, below that secondary standard, but if they do get to be around that secondary standard, we don't actually have to take action until they get as high as the primary standard. So I looked up some different ions, and I looked up copper. A lot of pipes have been made with copper, and copper has some interesting antimicrobial properties, which makes it potentially attractive for having copper pipes, but it also can be toxic. So it has a secondary standard of 1 milligram per liter. Now, this doesn't look like parts per million. It also doesn't look like any, sort of normal unit. We're used to dealing with things like molarity. But the great thing about this is that since this is in a mass unit, we can easily convert this into molarity. We can just convert mass into moles. And now we're using a unit in chemistry that we feel much more comfortable with. So let's go ahead and do it just for the exercise. If we have a 1 milligram per liter copper, it's probably copper plus. It might be copper 2 plus. Those are the most common ions of copper. We would first remember that we have 1,000 milligrams in 1 gram. And then we need to convert grams to moles, so we look up the molecular weight, which is 63.546 grams of copper per mole. And because I want to cancel out my grams, I put that in the denominator so I can see my units are canceling. And I'm going to have moles per liter, which is what I want for molarity units. So this would get me 1.6 times 10 to the minus, I had 6 on the brain. It's really 1 to the minus 5 molar of copper plus or whatever other ions we happen to have. All right, so we can see how to convert milligrams per liter into molarity units. So let's get back to our original topic, which was parts per million. So here's where we start talking about some approximations. So if we're talking about 1 milligram per liter, this is 1 milligram of copper per 1 liter of solution. And we're assuming that this solution is mainly water. And one thing we can remember about water is that water has an approximate density of about 1 gram per milliliter. This is true for approximately room temperature. So if we're a lot different than room temperature, we might have to deal with differences, but the density of water changes pretty slowly, so this is a pretty decent approximation. So if we go from 1 milligram of copper per 1 liter of solution to try and figure out what this is in terms of mass per mass, the reason why we are doing that is that parts per million has a flexible way of looking at it. We can do number of particles over total particles, so a counted moles, for example. It can also be mass of one thing divided by the total mass, just like we would do with percent. So if we start going into mass units, because this is in milligrams already, then if we assume that the density of water is approximately 1 gram per milliliter, let's try going into grams and grams. So we still need to get rid of those milligrams. And now for liters, we have 1,000 milliliters per liter. And in 1 milliliter, we would have 1 gram. And if we calculate this through, then we're going to have 1 gram of copper per 1 million grams of water. And when we look at these, our grams are canceling each other out. This is the same thing as 1 part per million. I guess we had 2 sig figs, so we'll keep 2 sig figs. So the short version here is that when we look at milligrams per liter in water, this is the same thing as parts per million. And so that's why the water quality standards are listed in milligrams per liter. It's just equivalent to parts per million when we're looking at solutions. So that's kind of useful to know. So we see parts per million, parts per billion in water. We also see this in the gas phase. And just as we are looking in the aqueous phase for water pollutants, in the gas phase we're usually paying attention to trace amounts of a gas, usually some kind of toxic gas, or otherwise some kind of a pollutant. So let's look at the EPA limit for ozone just as an example. Ozone has the molecular formula O3, and it is considered an air pollutant, and it's controlled in terms of your exposure. The exposure limit for ozone is 0.1 parts per million for 8 hours of light work. And it has this very interesting set of different requirements. So if you're doing heavy work, then the number of hours go down, or the number of ppm go down. So your amount of exposure kind of also will depend on how much you're breathing. And if you're doing light work, you're not breathing as fast as if you're doing some heavier work. Okay, so let's think about how much ozone is actually present in a room if we were around this 0.1 parts per million. And if you aren't sure, ozone is generated by welding most commonly. Lightning strikes are also another one. Anytime you have a high voltage in air, then it can ionize the oxygen, which can create some O3. And it's a reactive gas. It's corrosive. It irritates your soft tissues, so it's not good for you to breathe. And if you've ever been around it before, it has, people describe it as having kind of a metallic smell. And if you've ever smelt it, it's pretty distinctive, and you would recognize it again. So if we're talking about wanting to find out how much ozone is present, well, what do we want to talk about? I usually like to talk about moles. So let's find out how many moles of ozone would be present in some particular space. Well, if you haven't reviewed the ideal gas law, you probably should go back and check on that. So if we are talking about gases, we need to pay attention to things like pressure, we need volume, we need temperature, right? Because we've got PV is equal to nRT and we're going for moles. So we're going to go ahead and have to make, again, some more approximations. I'm going to go ahead and pick a room that is, I'm just going to make it a 10 foot by 10 foot by 10 foot cube, just to keep my numbers easy. For temperature, let's pick a pleasant 20 degrees Celsius. It's about 68. And we'll just go with atmospheric pressure, which is about 1 bar. We are being kind of approximate here, and so this is why I'm okay with things like making approximations and just leaving myself with a couple of significant digits. So let's see. So if we have a room that is 10 feet in cubic dimensions, let's convert that into a unit I can handle, like liters. So 1 cubic foot, if I look up that conversion factor, it's 28.317 liters. 10 times 10 times 10 times 28 is 2.8 times 10 to the 4th liters. Temperature always has to be in Kelvin for us to be able to do gas law calculations. So that's 293 Kelvin. And then I can pick a gas constant that is useful to me. So, 0.083145 liter bar per mole Kelvin is one that will help me get the units I want. So when I set up this calculation, the number of moles is what I'm solving for. So I will have 1 bar multiplied by the volume, and then the gas constant, and the temperature. And if I do this calculation, I'm going to find that my total number of moles of gas is about 1,000 moles of gas in this room. And I want to know how much of this gas is ozone. So if I have 0.1 parts per million, that means I have 1 ozone per million particles. So just like if I was using percent, I'm going to convert this into a decimal form. So that's 1 times 10 to the minus 7. And now I can just go ahead and multiply that decimal by my total number of moles of the gas. So 1 times 10 to the minus 7 is the fraction of ozone molecules. If I multiply that times 1.15 times 10 to the 3 moles, then that's going to get me that I have 1.15 times 10 to the minus 4 moles of ozone in the room. So this hopefully has been a useful reminder of how we calculate or how we deal with parts per million in 2 different scenarios, a water quality scenario and an air quality scenario. And as always, if you have any questions about this, please go ahead and ask.